Ladies and gentlemen, welcome to this new technical webinar provided by Roboze. Here is Davide, and the main topic is 3D printing for the motorsport industry. After a brief introduction, we will take a look at the most interesting superpolymers and composite materials for the motorsport sector, checking out the advantages that have been already offered by Roboze 3D printing solutions in some real applications. But first of all, let me introduce myself. I'm Davide Schiena, Head of Application Engineering and Customer Success at Roboze. I'm one of the engineers who develops applications alongside with the customers to help them to integrate our 3D printing solutions into their workflow. So if you have a new project and you would like to be helped in design or material choices, feel free to get in touch with me. But now let's get into this webinar topic. Motorsport has always exerted a particular appeal with its technology, engines, shapes, and aerodynamic staff, providing to be one of the main promoters of the worldwide technological innovation along with the aerospace industry. The vehicles which are involved in competitive events are optimized to achieve the highest performances in order to gain those few seconds that can make the difference between first and the second place. So week after week, race after race, everything is designed to be lighter, faster, and safer. And this search for innovation have brought motorsport closer to the latest additive manufacturing technologies, which are able to provide new solutions to the main challenges faced by this industry. How? First of all, design freedom. While traditional manufacturing techniques remove material from a solid block, 3D printing involves the deposition of material layer by layer until the final part is obtained. This process enables an incredible design freedom, resulting in printed parts with extremely complex shapes or internal infills that may vary in pattern and density. This means that the material can be placed only where it is needed, creating lightweight and strong models that may push the topology optimization concept beyond any boundary. For sure, in such an industry where solid assemblies and aerodynamic studies have a key role, mechanics requires a surgical precision, whether it is for production or research purposes. And for this reason, additive manufacturing must go through the control of the whole printing process in order to ensure the accuracy and repeatability needed for rapid validation of motorsport and parts. And finally, materials. Think about vibration, heat, engine oils, and fuel. In the motorsport sector, 3D printing must necessarily be associated with superpolymers and composite materials that not only guarantee an excellent relationship between mechanical strength and density, but also chemical and thermal properties that are suitable for the specific application of interest. Here are the filaments we can process with Roboze devices, and as you can see, the range is quite wide, providing a flexible solution that can adapt to any request. Moreover, the huge know-how developed for superpolymers and composite materials allows us to explore applications that involve high operating temperatures, chemically aggressive environments, and demanding mechanical performances, taking advantage of the typical properties of plastics, such as their low density. Right now, the most demanded filaments for the motorsport industries are carbon PA, PEEK, and carbon PEEK. Roboze carbon PA is a composite material based on a polyamide 6 matrix reinforced with carbon fiber at 20% in weight. The reinforcement enhances the main properties of nylon, such as resistance to abrasion and wear, providing it with greater thermal and mechanical resistances. For this reason, the filament can work up to 180 degrees Celsius, while from the mechanical point of view, it shows a tensile strength of almost 140 megapascal and an elastic modulus of 15 gigapascal, which is much higher than most other composites available for FFF 3D printing solutions. The good surface finish, the excellent strength-to-weight ratio, and the possibility of post-machining make carbon PA one of the most used materials in the motorsport sector for the production of finished parts, such as levers and pedals, chain stabilizers, and air deflectors. PEEK is a semi-crystalline polymer capable of combining good mechanical properties with excellent chemical and wear resistances over an extremely wide temperature range. It has been certified as a self-extinguishing and flame smoke toxicity compliant material, which is often required for racing. PEEK's molecular nature allows it to maintain creep, fatigue, and wear resistances even at temperatures that are close to 250 degrees Celsius, making it optimal for those applications that require reciprocal sliding parts. By the same, most acids, bases, and organic solvents do not affect this superpolymer at all at high temperatures. So the ability to work in chemically and thermally aggressive environments, along with the good dielectric and insulating properties, make the motorsport industry use PEEK for the production of electrical connectors and elements which are in contact with oil and gasoline, such as the head or crankshaft covers. As for nylon, the addition of a 10% in weight of carbon fiber reinforcement into PEEK matrix increases its mechanical and thermal properties, enabling metal replacement in some of the most extreme applications. So, chemical and tribological characteristics are quite the same of the unfilled polymer, but the elastic modulus and the heat deflection temperature are respectively boosted up to 14 gigapascal and 280 degrees Celsius, with a better dimensional stability and an amazingly low coefficient of linear thermal expansion. For these reasons, carbon PEEK provides an optimal solution for the motorsport sector, which takes advantage of the high strength-to-weight ratio to produce seals, tools, and finished parts such as its shields, intercooler inlets, or shafts and hubs. Now, people working in motorsport know that the workload rarely drops to quiet routine levels. To provide a rapid response to the different needs of this industry, additive manufacturing technology can be integrated into the entire product life cycle, from design to support, in order to reduce related times and costs. As previously stated, from a design point of view, 3D printing may play a key role by enabling the production of geometrically complex models, reducing the need for assemblies, and integrating new functionalities within the parts. Moreover, when multiple design production test iterations are required, the 3D printing of superpolymers and composites can accelerate both the prototyping and production phases. In the same way, additive manufacturing can be used for the realization of tools, jigs, and fixtures for assembly and quality control of traditionally manufactured parts, promoting the digitization of the warehouse or standardizing and speeding up the production process. Now, let's see some real application, starting from a very simple but important concept. A racing car is a system that always runs close to its limits. And for this reason, weight plays a key role, as it is able to influence every single area and every single sector of the car, from performances to road handling, from the vehicle setup to its safety. For example, a heavier car will necessarily have a longer braking distances, worse handling, a more critical acceleration phase coming out of a curve, and so on. As said before, when you match the design freedom provided by 3D printing with superpolymers and composite materials, you can obtain lightweight and resistant parts, which are able to greatly reduce the overall weight of the vehicle while keeping it safe. With a particular attention to the design phase, FCE Engineering has taken advantage of the metal replacement opportunity offered by Roboze, reducing the weight of a perfectly operative 250 GP engine of about 3 kilograms with respect to the original design that was mainly made out of metal. Different application, same goal. Here we have a study from the ETS Maker Institute of Fornovo, where the structure of a high-performance automotive brake caliper has been completely redesigned to be made in carbon peak using Roboze FFF 3D printing solutions. The braking system slows the vehicle down by converting movement into heat. This is done by applying pressure to the rear side of the pistons, which push the brake pads against the rotor disc. And the part that is mainly involved to support the clamping force is the caliper body, which has to be light, stiff, and must withstand operating temperatures ranging from 150 to 200 degrees. The caliper body is usually made of die-casting aluminum, and its CNC machining can last more than 10 hours for a final weight that is generally comprised between 5 and 7 kilograms. By applying some topology optimization and design for additive manufacturing concepts, along with the thermomechanical simulations for sure, the caliper body has been printed in one single step with a total weight that was lower than 2 kilograms. So if you're interested in this study, the printed part will be tested soon, so stay tuned. Then we can jump to a peak electrical connector we printed for one of the major world players in the automotive sector. As for automotive, among the trends you can observe in the motorsport industry, there is the electrification of the vehicle. Just think about Formula E, a FIA car series born in 2014, which is completely dedicated to electric cars. From this point of view, among the various solutions proposed by additive manufacturing technology, there is the possibility to realize protective cases and connectors with superpolymers, just like PEEK, which guarantee an appropriate electrical insulation even in challenging environments. This is particularly interesting when complex geometries and small production batches are required. So if you would like to learn more about this comparison between CNC machined and 3D printer connectors, I would suggest you to take a look at the dedicated white paper on the Roboze website. However, in a nutshell, with Roboze 3D printing solutions, it was possible to realize the same part in a single step without any operator during the production phase, and respecting a medium fine tolerance class according to the standard ISO 2768. This led to a total cost saving of more than 90%. And last but not the least, the carbon fiber lamination tools. You know that the flagship material of the resin division is the carbon fiber laminate, due to the combination of low density and excellent mechanical properties, such as stiffness and resistance to abrasion, fatigue, and impacts. Just Consider that whole monocoque frames are usually made of sandwich panels with carbon fiber outer layers spaced by foams. So there are many methods for the realization of carbon fiber laminates. Some of them involve a hot forming process followed by a polymerization of the epoxy resin in autoclave. To give you an idea of the pressures and the temperatures involved, I've reported them on this slide. Now, the damages suffered by a vehicle during a race or the structural improvements made during the development of a new frame and so on may involve the realization of many single parts in a very short time. With an industry that moves so fast, traditional methods for the production of invar or steel molds may be too slow, since they are often related to high cost and times. So the need to speed up the production process for carbon fiber lamination tools is shared by many industries, in addition to motorsport, including aerospace and defense. And for this reason, Leonardo Aerostructures has successfully experimented with the introduction of Roboze 3D printing technology to replace traditional molds with carbon PA and carbon PEEK, producing uprights and beam joints for the assembly of the keel frame of an airliner. Now, if you look at times and cost savings, you can easily figure out how to take advantage of this kind of solution for your own motorsport application. As you may have guessed, Roboze is a solution provider that offers its technical and operational know-how to provide a technological advantage to companies all over the world. Some examples are warehouse digitization, cost-effective mass customization, innovative solutions, rapid prototyping, etc., etc. And how we do this? By providing the most accurate 3D printers and the best technical polymers in the world, either by installing our devices directly at the customer's production plant or by offering a professional certified 3D printing service on the local area where it's needed. That's what we call Roboze 3D parts, and if you are interested in it, you can get a quotation directly from Roboze website. So now, if you have any question, there should be a text box for this somewhere in the chat. Thank you, Bruno, for the question. So Bruno asks, what is the accuracy you could provide, plus or minus 0.5 millimeters or 0.05 millimeters as example? So very well. As for any other production technology, for example, CNC machining, we refer to the standard ISO 2768. to stabilize the tolerance class we can get for a particular material or for a particular model. For example, a very large one will have a lower, a higher class tolerance with respect to a very small part. So generally, we can guarantee a fine tolerance class, which is pretty good. It's absolutely comparable to CNC machines. Then Derek Ellis asks, what is the timetable for the brake caliper study results? So Derek, okay, I will let you know. I have not this timeline schedule. I've not received this kind of timeline from the ETS maker. So I will let you know for sure. What parts are 3D printed? Okay, Tim asks, what parts are 3D printed in Formula One? Now, from what I know, there are different Formula One teams that use 3D printing to adjust the setup of the vehicle before starting a race. So I'm not able to say, I can't for sure say the name of these teams, as well as I'm not able to say which kind of parts are really used, are really hand-use parts for those kind of teams. However, generally, you can look at the air deflectors that are under the nose of the vehicle or on the rotor. So these are the most used parts, or inside the cabin of the vehicle. Then Damiano asks, is it possible to have the presentation? For sure. I would invite you to stay tuned because the white paper on this kind of topic will be soon available on our website, both in Italian or in English, and from what I know, French and German. So stay tuned. Friedrich asks, what support structures are used? Same material? Yeah, it depends. We have production printers, which uses two extruders, so they are able to print even with different materials. So the easy to break ones or the soluble ones. However, when you look at PEEK or carbon PEEK, generally you refer to the same material for the support structure because they are extruded at a very high temperature, 450 degrees. So it's quite difficult to find a couple of materials which can hold these kind of temperatures. Derek, you're very welcome. Then Rodrigo asks, what is the minimum wall thickness allowable? Okay, very well. It depends on the extruder you are using. We have 0.4 millimeters or 0.6 millimeter extruder nozzles, and generally we suggest to have at least two strands. So it should be 0.8 millimeters for the 0.4 millimeters nozzle, and you have to double even for 0.6, so 1.2 millimeters for the bigger one. Jerry, how long for Argo 500 to warm up and cool down after print? That's a pretty nice question. So you have to know that our heated chamber is quite particular because the air is sucked in by a collector on the bottom of the printer and then is heated up and is fed back through both left and right side panels. This bidirectional flow helps us to achieve the highest temperature we can reach on Argo, that is 180 degrees, in less than 2 hours. It is quite interesting if you refer to some other companies on the market that may require at least 6 hours to achieve the same temperature. Then, with respect to the cooling down phase, we integrate inside our Argo a thermoregulator that allows you to set up controlled cooling ramps in order to add to the 3D printing process thermal post-processing. This is quite useful when you have semi-crystalline materials just like PEEK or carbon PEEK or carbon PA, let's say, because you can associate the 3D printing with a thermal post-processing such as annealing. That is the best post-processing you can figure out to release any kind of residual stresses inside the printed parts. So it will depend, to respond to your question, it will depend on your propension to use or not the annealing. So then you can set up 10 degrees steps per hour, etc., etc. Frederick, and how do you get it out of a pipe? So the question was, okay, it is referred to the question that was about support structures. So how do you get heat out of a pipe? Very well, when you have to use this kind of geometries, of shapes, with those kind of materials that are not usable with soluble supports, let's say, you have to try to find out the best way to design your part. It's just what you do, for example, with CNC or any kind of traditional manufacturing technique. In this case, there are some very interesting design for additive manufacturing concepts you can apply to avoid the support structure needs. For example, instead of a circular pipe, you can do something that has 45 degrees chamfers and so on and so on. Otherwise, you have to split down your part into parts. Benjamin asks, is there any difficulties or complications of machining carbon PEEK? No, PEEK and carbon PEEK are easily machinable. For sure, you have to know which kind of tool, which kind of lubricant, and so on you have to use, but they are pretty easy to machine out, to mill, drill, etc., etc. Bruno, okay, asks, for example, a water pipe inlet at the entry of the thermal engine, inner diameter 38 millimeters, and I have external grooves for an O-ring seals where the general tolerance dimensions are plus or minus 0.05 tolerances. Okay, let me figure out what are you saying. So inner diameter. Okay, I think it's a straight pipe at the entry of the thermal engine. Very well. External grooves for an O-ring. Okay, very well. Where the general tolerance dimensions are plus minus 0.05 tolerances. Okay, it will depend on the material you're going to use. So generally, if you can achieve a fine class tolerance, you may stay inside those kind of values, because 38 millimeters is quite small. However, we could check. So if you are really interested in this kind of application, I would suggest you to send me an email, and we can do some kind of consideration looking at the STL or the solid part of your model. So it would be very interesting to me. So get in touch, Bruno. Then Friedrich asks, maybe I can print a flexible material for support and pull it out in wall length. Okay, Frederick, it will depend, because you have to find out the material that has this kind of temperature to work with. So it's not trivial. We have a research and development department that is working for sure on this kind of need, but right now there are no commercial solutions for customers or 3D printing owners. So hold on, maybe we can find out the best geometry, the best shapes for your project, if you would like to share it with me, for example. Bruno, you're very welcome. Okay, any other question? Very well. If we are done, I thank you for your attention, and I invite you to download the dedicated white paper if you like this webinar. So talk to you at the next technical focus. So, Jenny, okay, here I am. So 10 degrees per hour is the fastest cool. No, for sure you can improve it. Generally, the fastest cool rate we use is 2 degrees per minute, so 60 degrees per hour. If you're, I'm sorry, I miscalculated. So 2 degrees per minute. That means 120 degrees per hour. However, generally, when we reach the 70 degrees, we let the printer cool down by itself, shutting it off. Okay, hope to have been clean enough. Okay, very well. So again, I thank you for your attention. I invite you to download the dedicated white paper and talk to you at the next technical focus. Bye, thank you very much.